Welcome to more L'Hopital's rule examples. So recall from the previous video, we had seen that if we had indeterminate form limit as x approaches c, limit as x approaches c of f of x over g of x, that went to either 0 over 0 or infinity over infinity, then we had that limit as x approaches 0, or sorry, as x approaches c of f of x over g of x could be found by taking the limit as x approaches c of f prime of x over g prime of x, if that limit as x approaches c of f prime of x over g prime of x exists. So for example, if we want to take the limit as x approaches 1 of x squared minus 3x plus 2 all over x squared minus 1, if we plug in 0, or sorry, if we plug in 1, we would have 1 squared minus 3 times 1 plus 2, which goes to 0. And then down below, we would have 1 squared minus 1, which also goes to 0. We have our 0 over 0 situation. If we take the derivative of the top and the bottom, then we would wind up with the limit as x approaches 1 of, we would have 2x minus 3 up top and 2x down below. And if we plug in 1 to this, we have 2 times 1 minus 3 over 2 times 1, otherwise known as let's see, negative 1 up top over 2. Now, we previously found this limit by factoring the numerator and denominator and then canceling out that factor of x minus 1. This is just an alternative way to find our limit. Next up, let's look at limits at infinity. So if we wish to find the limit as x goes to infinity of x squared minus 5x plus 2 over 6x squared minus 4x plus 1, we could use our rules for the limit at infinity when we're dealing with rational functions, or we could use L'Hopital's rule. So if we plug in infinity, this will definitely give us an infinity over infinity situation. And so we can go ahead and take the derivative. So we're now looking at the limit as x goes to infinity of 2x minus 5 over 12x minus 4. Again, this will go to infinity over infinity. So we can actually apply L'Hopital's rule again. So now we have the limit as x goes to infinity of the top will be 2, the denominator will be 12, and we wind up getting 1/6, which is precisely what that rule told us. If the degrees matched, we got the leading coefficients, right? So again, here we are doing L'Hopital's rule once. So we applied L'Hopital's rule. And then again, we applied L'Hopital's rule. And now if we take a look at another situation, so in this case where the numerator has the higher degree, we already know from our rule that if the numerator has the higher degree, that the limit at infinity is positive or negative infinity. But we can go ahead and use L'Hopital's rule just to verify. So in this case, if we plugged in infinity, this would give us an infinity over infinity situation. So if we go ahead and apply L'Hopital's rule, we wind up looking at the limit as x goes to infinity of negative 20 x to the fourth minus 6x all over 4x minus 4. I apologize. Let me pause and re-update my screen. Once again, this is still an infinity over infinity situation. Whether it's plus or minus, I'm not too concerned with it at this point. So we'll go ahead and apply L'Hopital's rule again. And this becomes the limit as x goes to infinity of, we have negative 80 x cubed minus 6 all over 4. Now this is no longer an infinity over infinity situation. The numerator would go to a negative infinity. The denominator would just go to 4. So this limit winds up being negative infinity. So this is a situation where we ran L'Hopital's rule a couple times, but we didn't wind up on a number this time around, right? We just wound up with an infinite limit. One more time, let's go ahead and evaluate the limit as x goes to infinity of 3x plus 4 all over 2x cubed minus 5x plus 1. Once again, using our rules for limits at infinity, the degrees higher in the denominator, we would expect this limit to go to 0, but we can apply L'Hopital's rule just to check. So this would be an infinity over infinity situation. I'll go ahead and apply L'Hopital's rule. And if we take the derivative of the top and the bottom, we still have our limit of x goes to infinity. Up top, we will just have 3. Down below, we'll have 6x squared minus 5. This limit, we know the top will stay at 3. The denominator will still go to infinity. And so this does, in fact, wind up giving us a limit of 0. So this is limits at infinity. Here we were just using rational functions, which we did know how to take the limit at infinity of from prior algebraic manipulations, but this gives us an alternative approach.